we've had one opportunity where we had a meeting and we looked at the data and we compiled it, and we could see that there was definitely valuable data there, especially with the total volatile organic compounds. One of the things that Declan said he was still going to look at is to see if he could get the altitude readings that, because we wanted to see at what altitude did you start to get these significant spikes in the TVOX. We have not been able to meet again, but Declan said he was going to do something in order to get that, because we looked at the readings and was like, great, it would be great to know at what altitude you got these spikes. So that's where we are at the moment. I would have liked us to be a little bit further in our analysis, but at the moment, that's the reality of it. We haven't had opportunity to get back yet because we've obviously been involved with the ISS, but we need to do that.
Okay, great. I think that certainly Jim's students are going to be able to shed some light on
Yes.
that. Just hang on a second. I think
we also look at the acceleration. I mean, we looked at the three components of acceleration, and that kind of seemed to make sense. But we do need to look at it in more detail. And one of the things I was hoping is that we would gain maybe a deeper insight into possibly how we can do it better from this meeting.
Okay. No, that's great. I think that Jim, I don't know if you want to just come in here yourself. You found that the data was very spotty, the GPS data that was provided, and it really needed a lot of cleanup.
Want to talk about that?
Oh yeah, we found.
So this is Bridget.
Yes, my name's Bridget.
One of the students that did a lot. And that's Miko over here.
Hi.
And Jorvin.
Hi.
And Mark's not here right now, but he'll join later. But Bridget was getting excited because she thinks she can help.
Well, for the acceleration data, since it didn't come directly from us, we did find that it was more like the timing recorded more, not more sporadically, but it just had larger increments. So if we were to use that acceleration data, like combined with our data, we would just have less data points because it wasn't, we had to line up the different times because it wasn't in the same increments as our data. So
do you mean your GPS data?
Yes.
Yes.
Yes. And that includes like the altitude.
Okay.
Do you want to show? Judy, do you want us to show? If I can share the screen, I'll show the graph and she can explain what she did.
Please. That would be fantastic.
Let me look over here and try. Sorry, I got two computers here, one running the screen and the other running this. So give me a second. So let's see if I share this computer. Oh, actually. Perfect. Okay.
Oh.
Can we see? Okay, there's our presentation. Perfect. Okay. And now I need to find this. What is this?
Which one are you looking for?
I don't know. You tell me which one I'm looking for.
Slide 6 has the altitude graph.
Okay, here's the slide.
If we're just looking at the graph on the right, that is our time versus altitude data. And if you look at the descent of the balloon on the far right of the graph, we can see that the data points are much more spread out because of the speed of the balloon. And so we were saying we had to use Google Sheets to line up the GPS data with the data we collected for time, because we recorded data about every
second or two.
Yeah, every second or two, but the GPS data was recorded in much larger increments, like every minute. And so the data points are much more spread out because it was just at a different speed or in a different increment. So yeah.
So we meaning Bridget really added on to where the troposphere and the stratosphere would be in each graph.
Yeah.
So that's the added layer here, and the coloring in the data is cluster analysis she did with Python. So what that is, it just looks at the data and kind of categorizes similar data together. And so do you want to talk about what you found from that?
For the, like, so
these graphs, for example.
Okay, so yeah, for example, the pressure and altitude graphs, these were the first ones that actually really made sense to us. We were able to pinpoint exactly when the balloon was launched, reached float, and landed. And the cluster analysis showed each transition between atmospheric layers. And what was really cool to see is that it transitioned at exactly the same points on the way up and on the way down. So yeah, it was exciting because it looks exactly like it's supposed to, which was nice. We found that like our data aligned with previous flights and other data we found. And yeah, it reached float at about 38-ish thousand meters. Yeah. Do we want to?
Yeah, you want me to go to the next one?
Oh, sure. Yeah. So this was our the acceleration graph we made. It was just a magnitude over time. This one was exciting because we could also again pinpoint exactly the moments in time when it reached float, popped, and landed. At about 19,000 seconds, when our data started was when it launched, and that's that first spike in the troposphere in acceleration. And then it reached float or the atmospheric transition was about 21,000 meters.
This glob here is what she's talking, this area is what she's talking about, reach float somewhere there.
And then the most exciting part is the very right of the graph when we can see it popped and was accelerating downwards until it landed.
Yes.
So, yes. And then if we continue on, our temperature graphs were also they aligned really well with data from from previous flights and what is expected in the atmosphere. If we look at the graphs on the right, the one above is from Google, but it looks like it was really exciting to see that our graph looks exactly like previous data and what it's supposed to look like. The one thing about our temperature versus altitude graph is that on its descent, it's a lot sharper of a curve and we figured that it's because of the GPS data being recorded less often than our data was recorded, and so we could see that it's much sharper because of the change in speed as the balloon descended.
So you can kind of follow it. It starts here, and then goes up through the troposphere. Then you get this interface here, continues up through the stratosphere, floats, and then comes back down. This was an anomaly in their data we didn't take out, and it literally read the altitude was 0, but it landed at 5,000, whatever it was, somewhere around here.
Yeah, and we can see that the temperature decreased as it was going through the troposphere, and then when it reached higher altitudes in the stratosphere, it actually increased, which is what we expected. So, and then I think that's like for our basic data that we, yeah, like our basic atmospheric data, temperature and pressure and stuff. So, do we want to save the gas ones for later?
Yeah. We'd rather save, if anybody else wants to present, we'd rather save some of the gas information for Mark to come. He should be here in like 10 or so minutes. If that's okay. Bianca, did you want to?
Absolutely. Yeah, Bianca, please.
Oh, you gotta unmute, Bianca.
That always helps. Please go back to the slide with the accelerometer. So it could be nice if you, with this graph, had instead of time, or maybe also with time, had acceleration versus altitude. Because then it will be nice to see that big spike that you have after 37,000 seconds is hopefully when it was at the highest altitude. And after that it should kind of like come down. So that curve you have in the first graph where you kind of like show altitude going up and down again, if that could be overlaid with accelerometer, then we could see that that the balloon actually was at the highest altitude when it popped. So
yeah.
just, yeah.
Yeah, that would definitely be exciting to see. We do know by looking at, if you can go to the slide before it too. If we look at that altitude graph, the time at when it popped on the altitude graph does line up with the like 37,000 seconds. So like the times on both graphs line up, but it would definitely be interesting to see it on one graph. So like when it popped, according to those graphs, is about 37,000 seconds, and then if you go back to the acceleration, it's at that same moment in time. So
yeah,
I think it should line up, but it would definitely be cool to see it on one graph.
If you go to the next slide, was it next one, the one with the zigzag? This one here. So I mean, when it comes down again, I mean, I can see the timeline from the first graph where we see when the balloon pops. It like 80% of the time happened while the balloon was still there, and 20% of the time after the balloon popped, if I kind of like should guess. And that, of course, independent of the GPS, also means that you yourself have way less data when you're coming down, because the whole thing happens over a shorter period, which also kind of like explains why the curve that you have on your graph in the lower right corner is kind of like more smooth, simply because there's not too many zigzag points on the way down. I can also imagine that when it comes down, gravity will take that gondola a little bit more hectic down, and the parachute is like, it will be a smoother flight going down than going up, where wind and weather and balloon and pressure on a different altitude, if one can imagine that, with maybe different kind of like humidity levels and temperature levels and things like that, you will have that little bit zigzag going up, but going down, that's not going to influence the parachute in the same way that probably influence a balloon going up. So maybe some of that can explain it. I don't know, but just to give a kind of like helping clue here. But I really like it. It's great graphs, and I like how you colored in the stratosphere and troposphere, because it helps kind of like explaining, you know, those different zones. It's basically when you use your Google graph, where we can see, yeah, that's kind of like what the textbook says, and you're just proving that, which I also think is a very, very important, high school, even, university students, until they do a master's thesis or a PhD. That just proves stuff that happened before, and that it actually is real, the stuff we learn, you know. So I think it's great to see that you take the theory in, like you did here with the Google graph, and then prove with your own data, yeah, it wasn't a lie. It is really the way that the world works. Great stuff.
Before we move on, are there any other questions around this data from anybody?
If I can just jump in quickly.
Please,
Fascinating.
Richard.
I'm super impressed with what you have done. This is the first time I've ever seen anything like this. So really, congratulations. I applaud you. Astounding. And thank you for sharing this information with us. I think, unfortunately, that my team is not able to attend today. We have sports awards, big sports award event on happening in, I think it's about half an hour. So I do apologize on their behalf, and hoping that we will have another opportunity to share some of their findings. I know that they have been working on it. But really, Jim and team, well done. Thank you so much for running around in New Mexico for us. And, you know, we really appreciate the opportunity that you've given us. So thank you.
You're welcome,
Absolutely.
Richard. But we do have more data. Like, this is just the basic stuff, but we made we think a huge discovery to explain a lot of some of the anomalies we got.
Sorry, Jim, before you carry on and before you move off the slide, this that point where you had that anomaly, where it went to where you had the GPS data where it said the altitude was 0. We certainly have found that as well, is that sometimes the GPS will say latitude and longitude is 0, 0. So suddenly the balloon that was flying somewhere in North Carolina popped to off the coast of Nigeria and then back again. Because what it's doing is it's recognizing 0 as a data point instead of saying the packet was empty. So I think that if you apply some statistical methods, what you could do is you could say what constitutes an outlier. So that what you can do is then you can actually justify removing that point from the data set. And you may also find that you've got some squiggles on the way up, and that's okay because it's not too far away from the theory. So yeah, sometimes with these data sets, if you apply some kind of like sigma theory or whatever it is, it's literally 40 years since I did this stuff. But there are certain circumstances where you can say this is too much of an outlier, so therefore I'm going to exclude that data point, so that it doesn't mess up the rest of your theory, etc. So yeah, I would say for future presentations, I think what you can do is you can remove that data point very legitimately. I mean, Rick, William, what do you think? You're the professor. Would you allow that to be removed?
Yeah, like Judy, like you said, they are outliers. And knowing that there's some anomalies in the
about
data.
right here at above the 15,000, it cuts out again, and it doesn't begin here until it's like 0, and then it comes back. So it's just so
if it's bad, if it's bad data, then you remove it. As long as you can say, yes, I know it's bad data, and this is why. Because there are always going to be outliers. And on the way up, you could probably even put in averaging, do an averaging window. and that would smooth it out. But, you know, you can see that if you were just to draw a line, it matches up. And so one way to do it, and this is probably what Google, wherever they got this, they took an average of 10,000 points
Right.
and said, okay, this is the curve that fits it.
Yeah. Yeah. I think some of the squiggles are probably right or indicative of something. Let's say that from some other graphs that we have. It's
Right.
actually, I think, traveling through different, I think about here, somewhere about here is where it starts traveling through different air with different profiles and stuff. But yeah.
Yeah, I mean, you could have what, like you said, different jet streams. If a jet stream is up there, that you might have caught.
Well, it's funny you say that, William. Yeah, there is. Which we just discovered yesterday?
2 days ago, yeah.
2 days ago, at the end of the day. So, yeah, there might be an explanation.
Yeah.
Don? Sorry, Don, you were wanting to say something. Sorry, I interrupted.
I just, firstly, I want to follow on from Richard and just commend your team for the level of analysis and, you know, your presentation. I said to Richard in our WhatsApp that this is definitely our first radio, and you know, the standard of feedback is superb. So I would really want to ask you that we can learn from you, because we obviously still want to fully analyze the data that we have. And would you mind if we sort of knocked on your door, as it were, for some advice and some guidance? Because there's definitely a very much higher level of analysis than what I think we have been able to, you know, certainly engage with the data thus far. I'm not too sure whether you collected way more data than us. We're privy to the same data. Are we privy to the same data?
We're good.
Yeah. So your group has their data, but I think we shared out the folder with everybody's data.
Yes, you did. Yeah.
And this is just our data. We haven't looked at anybody else's yet. We were kind of hoping to get a sense of, like, did other people see the same things that we were seeing? Because we had the carbon, the air quality sensor on there and stuff. Yeah. So that's where some of the interesting stuff came from, observations in there.
Yeah, this is just our data combined with some of the GPS data. The only time we really used the GPS data is with any graphs where we had altitude in it. Other than that, it's all our own data.
And
I think
Bridget just did it in Python, so it's not it's not a special program we did. She can probably walk you through.
Sure. Yeah, our team leader, I'll definitely get our team leader to communicate with you. But so I think the thing that we were waiting for, and we just haven't had time to get around to it, is to actually take the data from the GPS, the altitude data, and to actually then sort of correlate it with the data that we had. We were in particular looking at the TVOC, you know, the organic compounds, because we definitely saw there was definitely non-trivial data there. There was definitely a massive spike in those readings. And we want to, I'm really interested to see what your analysis is of your data, because the first thing I said to my team was as well, we definitely need to look at what altitude that took. And I mean, as I'm sitting here looking at your presentation, which is superb, I would love to see where it actually, that layer, where it's actually, it seems to be sitting in our atmosphere, whether it's in the troposphere or the stratosphere, where it is. But that's what our next step was, to actually get to that. So this is great. Thank you. Thank you very much.
Bridget, do you want to go
Yeah, we can talk about
We
our.
can talk about, like, I think you probably got a similar spike, right?
Yeah.
Okay, see, it just wasn't us.
That's-
I thought it was like something funny when I was looking at it. I'm like,
Yeah.
something happened here, but then
Yeah.
2 days ago,
Yes.
I think I was reading something and it just clicked in my head and I'm like, wait a minute, I think I know what can explain this.
Yeah, we were looking through all of our gas data. Like we had our like basic temperature and pressure out of the way, and we were looking more about our levels of gases in the atmosphere. Can you actually go back one
Back
slide?
one?
Yeah, so we had a air quality sensor that did hydrogen, ethanol, carbon dioxide, and also the volatile compounds. And we were looking at, for our first ones, we saw hydrogen and ethanol. We actually had a negative spike in the atmosphere at the same time that the carbon dioxide went way up.
You're speaking about this.
Yes, yeah, in both graphs as well. And so the first thing we noticed is that in the ethanol, as we started rising through the troposphere, the ethanol went up, which we discovered is because of an increase over the past several decades because of the Clean Air Act amendments of 1990, which Mark knows more about, but that's okay. So for the most part, these gases originally kind of aligned with what we were looking at, like a decrease as you go up through the atmosphere. But then the negative spike was really like an anomaly that we were looking at that we couldn't explain at first. And so we didn't think much of it until our later graphs gave us more of an indication, which I'll talk about in a minute. But we figured that it decreased at those points because of like a possible chemical reaction in the atmosphere where the gases are competed out or used up. But if we look at the carbon dioxide graph, this one was the graph that told us that something was very clearly different than what we expected, and it was more than just bad data because of the like gravity of the spike. So at higher altitudes, carbon dioxide, or especially this where the balloon floated, carbon dioxide is supposed to remain relatively constant or even decrease slightly. But obviously we had a very big spike in carbon dioxide. So we realized that the balloon either encountered some smoke or another carbon dioxide dense patch. And so this would also explain why the previous declines in hydrogen and ethanol happened with. So we were looking more into like what this could be in the past couple days. And so, but if we go to the UV.
Well, what altitude is this at?
Oh, this is at
This is at float, so about
yeah, this is at
24 miles or 38 kilometers. This whole region here.
Yeah,
This is where it kind of pops here and it starts coming down.
Yeah, the balloon floats from about like from the 25,000 seconds to
Yeah, so
37.
this is all float here.
Yeah. So at like in the second half of its float time, it hits some sort of carbon dioxide dense patch. And then the other graph that was especially weird for us was the UV index graph. We had a light sensor on our payload that would measure the UV index, and we definitely expected it to go way up, especially as it passed through the clouds and reaches float, but instead it went way down. And so we, it greatly contradicts our expectations. So the decrease, it lines up with the spike in carbon dioxide and also the decreases in hydrogen and ethanol. So we definitely knew at this point, especially since it came from two different sensors, that some sort of anomaly happened in the second half of the balloon's float, whether it hit like a carbon dioxide dense patch, but yeah. So. And then these were the most recent graphs that gave us like again lined up with our anomalies. we had a BME 688 gas scanning sensor on our payload, and it did not record data in the way we anticipated, but we were still able to look at gas resistance. So lower gas resistance readings, they indicate poor air quality. And although gas resistance, you would think it kind of goes up in the atmosphere, it definitely told us exactly where we hit like either smoke or something else. And the gas resistance goes way down when the carbon dioxide spikes, which lines up, and it's from 2 different sensors. So again, we were looking at how like those anomalies line up. The other thing is that this is our volatile compounds graph, and the spike starts at about when it reaches float, and it stays very high throughout the second half of the float. And yeah, so that was our volatile compounds. And since we ended up coming to the conclusion that it passed through some sort of stratospheric intrusion. And in the past 2 days, we've been looking at what this stratospheric intrusion could possibly be. So if we go to the next slide. So we have been looking at, and this is just our theory. It's not necessarily true, but we have evidence to support that it could be true. So because of the spike in carbon dioxide in particular, we were looking at events recently that would release large amounts of carbon dioxide into the atmosphere. And one thing that we put together, or Mr. Gorman indicated, is that volcanoes actually, they release a lot of carbon dioxide, and the other thing that they release is sulfur dioxide, which interacts with UV, and that would explain why the UV index went way down if the balloon was recording data from volcanic emissions. And so we started looking at recent volcanic activity, and we found that the Great Sitkin volcano in Alaska has been very active over the summer. Its last large explosion was in May of 2021, but over the summer it has been having lava effusions through the summer, and it had a pretty great one between August 13th and August 20th, right before our launch. And so the next thing we were looking at is it possible that we recorded these emissions in New Mexico? So if we go to the next slide, we discovered that the jet streams in the atmosphere, and also the atmospheric movements, follow exactly from Alaska into like southwest US states like New Mexico and Arizona. And we found that the top left graph is a trajectory path of the effusions that are still occurring from the Great Sitkin, and those trajectories head directly towards New Mexico and Arizona. These are current ones because we haven't yet been able to find previous ones, or we couldn't get them into the slide because we figured this out recently. But the current jet streams line up with the jet streams from the few days before our launch. And since the trajectories of the emissions follow the jet stream path, we've made the assumption that the emissions from these spikes in our data could very well be volcanic emissions that the balloon ran into. So yeah, that's our theory, but it could be something else. So yeah.
So one thing you might want to check, and this is just a guess on my part, and what you've done is great, is what about contrails from particularly those military planes that get very high up? It's just something else because you are in that area where there's probably a lot of Air Force activity and testing.
Good idea too.
Hmm?
Yeah.
I didn't hear you,
since
Joe. Oh,
Oh, I said, that's a really good idea. We'll have to figure out how to do that.
yeah.
you have to probably
were,
have clearance.
Probably.
So yeah, we were looking at yeah, we only discovered or made the connections between all of our gas scanning graphs. So we haven't had the most time to look at everything, but this was just our first series, so we decided to run with it. But yeah. So yeah.
If I may
And
just
Mark
quickly
is here.
add.
Oh,
Yes,
yeah,
great.
Judy.
Yes, Mark, welcome. We saw you come in and sit behind Bridget. So, William, I agree with you. Fantastic idea. What I like about the volcanic explanation is the sulfur dioxide absorbing the ultraviolet light or blocking the ultraviolet light. So I think that, that's also quite a nice thing is, when one has multiple data sets, is to see how many of those anomalies or factors can be explained by different aspects. I actually don't know what the fuel is that they use in those planes, but maybe it is a sulfur strong fuel. One never knows. So that they could also be leaving behind some sulfur dioxide. But yeah, this is completely mind blowing. I'm so fascinated.
Yeah, once we discovered this, it became a little
Exciting.
We were all giddy about it, trying to figure out. And then it was like, at first they looked at me like I was crazy. I'm like, no, sulfur dioxide would do. And that's the thing that clicked in my head. I'm like, wait a minute, if it's emitting sulfur dioxide as a volcano, and then it would interact, that would explain the O3, just a lot of like things that went together. And I'm like, maybe, and then it all started making sense. So we'll have to like continue. We were going to reach out maybe to the weather lady that was part of this outlet and see what she has to say, what data she could maybe provide us, because we were trying to look on our own, but I'm not a meteorologist. I don't know. Like when I'm looking at the data, I'm like, I don't even know where to begin.
Yeah, we didn't realize how impossible it is to find jet stream data from the past, because you can either find it from like the early 1900s or today. Like it took us a while to figure out how to go back like a month, but yeah.
So Mark wants to.
So aside from the like volcanic plume, which don't get me wrong, has been absolutely incredible and a very interesting focus. When I saw the graph, one of the first things that I noticed was that the
little microphone back.
one of the first things that I noticed was that the ethanol seemed strangely high in amounts compared to what I was expecting. And in order to look at that data, I started doing some research. I went on to Google Scholar and started looking up atmospheric compositions. And I found out that ethanol is a rapidly increasing in quantity in the atmosphere for a variety of reasons. I ended up going down a rabbit hole where I pulled up a bunch of graphs from the US Department of Energy. But what I found very interesting is that the amount of ethanol in the atmosphere currently very much correlates with it was the Clean Air Act, I believe, of 1990, which stated that areas with carbon monoxide poisoning or enough to the point where it was harmful for humans had to replace a certain percentage of their fuel with ethanol. And additionally to that, corn-based ethanol is being used in a lot of different fuels. And I thought that was really interesting. And so I've been going down and looking at how this chemical change in the composition of the atmosphere would affect certain things. It would not cause significant changes like carbon dioxide or methane does directly, but ethanol in the atmosphere does mean that there is a different chemical makeup that could interact with volatile organic compounds, volatile sulfuric compounds, and it could cause some negative changes, but interestingly, it also causes positive changes to carbon because ethanol does not contain carbon. It is an oxidized fuel instead. So it improves the environment in certain areas, but changes the environment in the overall area, as it is improved air quality in certain places, but it's also overall changed the air composition in other places that didn't have that ethanol mandate. So I have been digging more into that to see if this rise in ethanol is a significant concern or an impact that should be like explored further, or if currently ethanol is a better solution than gasoline is for carbon emissions, if we want to focus more on those oxidized fuels are better for the environment in the short term. Anything else to say, Gordon?
Are there any questions on that? Hopefully, Don, you guys are finding similar things.
It's I feel a bit like Haas versus Red Bull in the F1 here. Your analysis is completely on a totally different level. I am truly humbled in a good way by what I'm seeing. It is phenomenal. I wish my team were here. They're definitely going to watch this recording to see what is actually what the standard is. Jim, what I want to ask you is, I mean, if I look at this, this looks like this is a major project that you do as part of your official school curriculum. Am I right in saying that?
No, these are these are independent research students / engineering 2. So for like Bridget, it was a lot of data analysis. So she's also in the computer science. She's big into that. So it was applying those skills in engineering to this project. So she learned a lot. It took her, was it 2 weeks to get it, to figure out how to actually get the data in the format she needed for the Python to interpret it and the code to work properly. So at some point we can get together, probably have a Zoom call with your students and us.
Yes, definitely.
And coordinate and kind of like walk you through the process of what we did so you could kind of replicate that. Because I mean, it's not, I don't know how to do all the Python stuff. This is the kids. Like, I just knew, hey, let's do this. We got to dig deeper here. You know, with a little bit of AI help, we were able to like guide us through the process. But definitely, we definitely need to do the altitude versus, you know, CO2 and that type of stuff. I think that'll give us another view of what's happening, a more clear view as well.
The data analysis, the actual making of the graphs is not difficult at all with Python, because you can just copy and paste the same code for each graph and change like the X and Y coordinates. It's the really hard part is making sure, one, that it can read, the Python program can read the CSV files easily, and the other part is actually getting the format of the CSV files, what you want, so it reads the data how you want. Yeah, so it definitely took a while to figure out, but it's easy to understand now, and so I'm happy to help with anything if you want.
We will definitely be learning from you. But I think one of the question I want to thank you for that is, I want to know, do you do this as a senior research project, which is formally part of your offering at your school, or is it done as a club? Is this sort of like just you do it because you love it, like we're doing it at our school? As a teacher, I'm asking.
It's just part of their like class. This is the project they decided to do in engineering, or part of their class. A couple of them have a independent research
Okay.
class.
Okay. Now
is what they
you've
call
answered
it.
my question.
Choose what they want. And
Yeah.
I don't see the four of them all together at once. I only see two together, and then another one at another point, and another one at another point. So it's hard to get them all to coordinated, right? That's another thing that's taking
We
a while,
manage.
because they have bits and pieces they're working on, but then we need to get together and actually share that information. So yeah, it's an addition kind of to what we're doing. So
Yeah, for me, it's just a part of my engineering class. Mr. Gorman like allows us, or the engineering class has a bunch of different projects you're able to work on that connect you to like real world experiences. And for me, this was
Yes.
just my project that I've been working on this year. So
Fantastic. Well done. Well done to you. And I mean, we can only learn from you. And I mean, if I look at your analysis of the gas analysis of how you were able to actually pull out the various gases, I mean, we didn't get anywhere near that yet. And I'd love for us to learn how you actually did that, the carbon dioxide, the hydrogen, the ethanol, and that. So yeah, we will definitely be knocking on your door to learn more from you. So thank you very, very much. This is absolutely awesome.
Jim,
Yeah.
please show the slide with your kids. You had a slide where you
yeah,
well,
here we go.
so if I can just talk to it on a general, so this is the kit that you guys flew, and you can see there's a red thing in the middle there. So that's a spark fun sensor. This is the BME 688, and that was put on a prototype board, which is one of those boards that have a little bit of wiring. So I'm having a similar board I'm holding up here. This is another sensor, and there's some wiring here. Now, next time you want to do this thing here, we have this new chip here that have the same connector that there is on that. So you will be able to connect it like that. And then I don't have the cable, but you can just put the cable in, and there's holes here for 1 inch distance, which both Adafruit and SparkFun typically use. And then you can connect it like that. But it's going to be better next year because we have 3 new prototypes that we're going to come out with as advanced kit. They are like more expensive, so that's the reason. But if you're going to fly in a balloon, then you can probably afford that. So the BME 688, we actually have planned to have that as an advanced weather sensor. So you will be able to use the BME 688 to get more data like that. And then the other sensor we are also going to do is that we're going to do an accelerometer that's called LSM9DS1. And that is an accelerometer similar to what you have that do acceleration X, Y, and Z. But it also it's also a magnometer that do X, Y, and Z, and it's also a gyroscope that do X, Y, and Z. So it's called 9 degrees of freedom. So you'll be able to pick up more movement on the balloon and kind of like use it to kind of like see how the balloon moved and so on. A thing you can do when you have proper GPS data and things like that is that you can do what's called a KLM file, I think it is. It's a file that you can load into Google Earth. And then you can actually use that and take Google Earth's camera view, and you can then see how it flew, like if you were sitting on the balloon. We've done it with some of our early balloon flights. It's actually fantastic. You feel like once you get all that right, that you're sitting in a balloon and you're flying. So that was a 2 sensor. Then we are working together with University of Cape Town with their radiation lab. And they have asked us to make a sensor for gamma radiation. So they have this little tiny sensor here, which is it can pick up gamma radiation, and it can also do neutron particles, I think neutron particles. So we're busy doing prototypes for this thing here they have a whole kind of like kits they have built together where they can count this radiation. But this one here is kind of like big because it uses a tube that requires like 300-400 volts. So that's a big step up on that. While this thing here requires 28 volts. So we're basically putting like a little chip together that provides the power, and then it counts the photons that hits this sensor here. So you'll be able next year to do that. And then what we're also going to try to do now that we have, this was our second flight, now that we have a lot of experience with this thing here, we're going to negotiate with the NASA team that you can, of course, put your camera on next time, because your extended core have a camera port. And if you put, and this one here is like 11 centimeter long flat cable, so you can have this, mounted so it sticks out and not look up to, the board above you, but out to the side. And then we can make sure that all the individual layer you can and you can shoot, like, you could shoot video, but it's probably better to do a high resolution picture, like once a minute or something like that. And then you have that. So if you, for example, had picked up, let's say, military aircraft, not that I think you will be that lucky, but you'll maybe be able to pick up a smoke cloud or something like that as you move up and down in a layer. So that might have been an opportunity. One of the nice things about using camera is that when you get to 48 kilometers, actually when you get to 20 kilometers and then above, then the atmosphere is so thin, so it looks like you're in space. It's like black when you look up. So like when we look out the window in an airplane, they're still like, white above us. But when you get to the altitude that this balloon flies in and floats up there, you get to an altitude where it looks like space. It's like black above you, even though it's completely daylight. Obviously, you are not even halfway into space, but for the purpose of a camera, you certainly look like that. So those 4 sensors, so the BME 688 that you've been using here, the LSM-9DS1 that we actually have been using internally here for many years, the gamma counter, and then the camera will allow you to do a massive more amount of data analysis next year. So for you at Parklands, if you want to kind of like work in like the same kind of sensors, you can of course do the same thing as Nipmuc have done here with the BME 688. But as I said, we're gonna do a chip that have the sensor on, so it makes it easier. And of course, you can always find other sensors that's going to be more interesting and put other stuff on it in the future. But very impressive.
Yeah, Bjarke, it looks really good. I mean, I'm more on the physics side of things. What you're talking about, I got the sense cosmic radiation, gamma radiation. Those are the kind of experiments we would certainly like to do if we get the opportunity to do this again. And hopefully we'll have learned a lot more about data analysis by the time we do it again. We'll have to have a crash course before our ISS mission.
Great. I think that we've got like a minute. I'm sure some people would like to just stay maybe a little bit longer. Jim, you and your students actually went to New Mexico. And I do know that you were able to give William very, very thorough feedback for the team at NASA. So hopefully they haven't taken that too personally, so they're going to let us fly again.
No, Christy actually gave us some feedback after I sent Jim's very detailed feedback, and she said perfect.
Great.
Wonderful. So we didn't ruffle any feathers, and I didn't point any fingers.
That's perfect.
Jim sent this to me.
No, that's absolutely great. Yeah, so I think that I mean, Jim, I'm not sure if we should go through all of that detail of, you know, your what you experienced there, or maybe what I should do is actually take the feedback that you sent and put that into some kind of report and share that with everybody. But I mean, there were some things that worked and some things that didn't work, that, you know, we should really consider for next time.
Yeah, I think like it was a great experience, right? The report I was asked to like give feedback on were specifically on areas where they could improve. So I think just sharing that gives like a not so good light over the whole thing. But overall, how did you find it, Bridget and Mark?
I thought it was awesome. I mean, we didn't actually get to see the launch because school was starting, but it was really cool to be in that environment anyway. Like, being able to like look at or attend the weather briefings and to be able to attach the payload. So it was really fun.
Did you get a chance to visit and eat the food around there, which all that was interesting from a cultural standpoint?
Oh, yeah.
Yeah, I think Mark and I drove 1,600 miles. So it was a ridiculous amount in like a few days, but
yeah, my family, we turned it into our family vacation for the summer. So we actually went to the Grand Canyon first. So we ended up driving like 2,200 miles, which on a rental car, but yeah, it was fun.
Yeah.
Yeah, it was a very good experience overall. Very, very good experience. There are just some things they could tighten up and, you know, do a little.
It was more of a logistic thing than it was a. Yeah.
Yeah.
And I think Christy took it as that.
Yeah. Yeah, because overall, the people out there were nice, were great. Colby was excellent. You know, he handled the whole package, you know, getting it back to us. Like, there was no problem, you know.
Right.
And that's what I was most worried about, how that transition was going to go, was going to remember to charge it and all that stuff. But he followed exactly what I wrote down, and it worked. I was never so pleased as when I got the package and we figured out there was 12 hours of data on each card. I was thrilled.
Big
So,
big zip files.
Big zip files, as Mark was saying, yeah. Yeah, so it was a very good experience. Definitely learned a lot.
Absolutely. I think from my side as well is that it's a really good experience to be part of an operational project or site, because yes, we learn all of these things in theory and we go through the safety training and we go through all of these different things, but when you're actually on site, as an engineer, you realize that oftentimes it's actually very difficult to get these things right. And you know, I mean, the thing is that, you know, I've had many years experience in the mining industry and the pulp and paper industry, in very heavy industries where safety is really, really an issue. And I think that probably what you experienced as well is that everybody can be told that they need to wear their PPE and that they need to do things in certain ways, but it actually needs to become part of the culture, and it needs to become a habit that you don't take a drill out before you've put your safety glasses on, etc. And, you know, I think quite often what happens is that Bianca will laugh at me because I'll get into the car and then I'll put my seatbelt on before I even turn on the ignition. It's just one of those things that I've been trained, you know, safety first before operating anything. And so, you know, what you saw there, this is something that they only do once a year. They're only out there in New Mexico once a year. And so all of the rules get forgotten because they're focusing on the task at hand. So it's something that you can take, into your careers and into industry is, a lot of these things actually have to become part of the culture. It's not good enough just learning things. It actually has to be part of the way that you behave, so that it can actually be, inculcated. But yeah, Jim, it's important to point it out, because if Christy's not there, it doesn't matter how much safety training one goes through, on the day, are people actually operating in a safe way?
Yeah. It wasn't like they were doing anything dangerous. It was just a poor example, to students that are coming and learning, and here's what it is. They kind of looked at me like, what? I'm like, just go with it. Like, just wanted to put it on. So,
Absolutely. So we have people having to leave. Please, any more feedback? Thanks, Don. Thank you so much. We'll see you again soon, very soon. And Ifriki, would you like to come with some feedback from your side? Okay, maybe Ifriki's got a bit of a weak connection. Okay, so that's great. So Bianca, William, Jim, are we doing this again?
Yeah, I already have a team.
Yeah, we're gonna do it again. One of the goal with this thing here was, of course, this flight here on that we're doing with New Mexico is every year in August, and we're gonna do that. What really inspires me is that there's a lot of data and a lot of learning to pick up. You did it with what, 5 sensors, or did you have 6 sensors on board? And you did the software development and got it up and running. And now that we have had our second flight with NASA, we become like regular, and it's going to be easier for us to get flights with them. They do other flights that could be interesting over the during the year. So they do 3 other flights as far as I know of. They do some flights in New Zealand. So they fly there. I don't know from to, but New Zealand is the word. The other thing is they fly over Antarctica, so over the South Pole. So they have a flight there. I think they launch and land there. It's quite a big continent. And then they have an interesting flight where they launch in Sweden, and it goes over the Atlantic and lands in Canada. So some of these flights, of course, not like a couple of hours. They're like maybe even a couple of weeks and things like that. So if we go on board some of these flights, we have to figure out how we get power from them, because I can only imagine they have solar panels or some serious power solution. We don't use any kind of power compared to all the other stuff. There's a gondola, which you guys have seen. So you can imagine that the little power we need should be available. So we're gonna try to figure out from them how we can, interface to their spare power supply in the future. That will make it much easier and guarantee that ours is operating and things like that. I think you guys have done this great analysis. I think that NASA is quite impressed with the data you got out. And I think that once they understand how beneficial it is for you guys, then they will, really, really appreciate if we fly with them again and get more institutions to go along with this thing here. So yes, normally the first 3 times we do anything, we call it pioneers. So you were in the second pioneer year, you're probably going to be in the third pioneer year, and then it's going to be very regular after that. So yes, we're going to do it again. It was we wasn't sure, but we got the data. In the next version, you will be able to install an extra SD cards on your board, so you can have 2 SD cards, so you can kind of like back up the data just in case that we hit something up in the altitude that could be dimensional to the data. And of course, there's other that will fly, and they will have equally a good analysis of data, or at least access to data that we can all share. We also try to make sure we have a TPS on our own. So we have a TPS where we pick up data every second, which is, 1 hertz is kind of like fine for TPS data, and then we can pick that up and store that in a comma separate file. And of course, you could also pick it up yourself if you choose to put a GPS sensor on. So that's also a possibility. There is a GPS sensor on as a X chip, so it looks like that, and it works. We've been using for a lot of time for balloon flights, smaller balloon flights, and things like that. So you have that opportunity. So yes, that's it from my side. We're definitely gonna do it again.
Yeah, the only thing I would add is there might be some experiments coming from others that might require them to be at either the pole or the southern hemisphere. And so by adding more chances, we might actually be able to pick up more, particularly at the university level. Because I know UH wants to test out one of their gamma ray sensors that they're building. So put both of them on there and do a compare.
Yeah.
Yeah, absolutely. So UH is University of Hawaii.
Oh yeah, excuse me.
Yeah, no, absolutely. So I think that's great. Is it okay if we close out the session? Congratulations, team.
Yes.
NICMAC, really, congratulations. Yeah, you've left everyone in the dust, okay? That dust that was in that box, Mark, when it was opened.
I'd rather look at it, Judy, as raising the bar so everybody can come up. Hold on.
Yes, sir.
Yeah.
Right. Now, I look at it as not like leaving everybody in the smoke of like, here's what you can do, right? We can get them there. It's now that we've plotted the trail, we kind of know a little bit more of what to do. And so it'll be kind of exciting to work, hopefully link up with Don and Richard's team. And I was kind of hoping Princeton was going to be on here and see, because they had a different set of data and what that might actually shed light on. Because looking at their data, we don't even know what it means. It's in bin files and stuff. It's not like CSV. So I might reach out to Mike and find out, but that might be something interesting to follow up on. But definitely, like, I don't know. This is just what we did, and we're happy to show other people how to do it so that in the end, everybody ends up with really good skills and really good presentations. You know, it's all about the science.
Exactly. And the fun. Bjarke, next year we have to be there.
Yeah, I can hear that.
Okay, wonderful. Thanks, everybody. Please have a wonderful rest of your morning.